Hello, welcome back to our lecture video. So let's have a new topic, addition of vector quantities. By the way, this is not a new topic. This is still a continuation of our physical quantities topic. But before going to addition of vector quantities, let's first have a review of scalar, and vector quantities. So let's differentiate what is a scalar. Scalar quantities or physical quantities require only magnitude, while vector quantities need magnitude and direction. So to explain or to differentiate further, let's have a specific example. So under scalar, we have example mass. Why mass is under scalar? Because example magnitude of mass, 2 kilograms. So the information 2 kilograms is complete. There is no need for you to ask in what direction is your 2 kilograms. Since this information is complete with magnitude only, then this mass is under scalar. In comparison, weight is under vector quantity. Why? Weight has direction. Weight should be directed downwards or towards the center of the earth. Why? Weight is the measure of the force exerted by the earth pulling a specific mass. So weight is a directed quantity. So it's the reason why it is under vector. Another example, force. Where do you think the force should be under? Force should be placed in here, under vector quantity. Why? Because force, example, you are asked to exert 100 Newton of force. So can you execute directly? You need to ask, in what direction would I exert such 100 Newton force? So information and the magnitude of force is incomplete. So force needs direction. Another, distance. So distance would be classified under, where do you think? Should be placed here. Distance. In comparison, displacement is under vector. So what's the difference? Okay, so example. If this is your initial position, I, and your final position would be here, F. So if the particle follows this path, particle moves up, down, then sideward, then down, up, down, before coming to its final position. So this green represents the distance, D. Distance. Where is the displacement? Displacement is a directed quantity. So if the direction upward is positive and the reverse downward is negative, and if going to the right is positive, then going the other way to the left is negative. To sum, the sum total of all these directions, the up and down, and up, down, minus down magnitude, and then left, right minus the left, then the total should be from the initial position to this final position. This now is our displacement. Okay, this is now our displacement. So displacement is a directed quantity. So simply the distance from the initial position to the final position, and straight line. So what else? How about time? Where do you think time belongs to? Should be placed here. Time has no direction. Let's take a look at this table. So in here, the sample scalar quantities, the distance, speed, mass, time, pressure, energy, volume, density. Vectors, we have displacement, velocity. Because velocity, it has direction, whereas speed is just a measure of how fast or how slow the object is moving, while velocity, it requires direction where the particle is moving aside from its magnitude. And the weight, acceleration, force, and momentum. These are the sample of vector quantities. Adding scalar physical quantities, it's very easy. Why? You will only use arithmetic, a simple addition. Example, mass magnitude 2 kilograms plus 6 kilograms. So you can directly answer as 8 kilograms. Simple mathematics because there is no direction. But how about vector? Since there is a direction, it involves direction, so that complicates. So let's have a sample. Okay, so there are other ways or different methods in vector addition. So we have graphical method. Under graphical method, we have parallelogram method, polygon method, and also analytical method. So under analytical method, we have Pythagorean theorem method. This is special case for vectors forming right angle. And the sine and cosine law, the component method. And for number 3, we also have experimental method of vector addition using force table, pulleys, and weights. Okay, but before going on further using graphical method or parallelogram or polygon, let's represent our vector graphically. So how are we going to represent a vector? So sample, a force vector. The given force vector is 5 newtons, then eastward. How are you going to represent this one? So let's represent our vector, force vector, by this arrow. So 5 straight, so going east. So this is direction, and 5 newtons. So if we are to use a scale, sample in 5 newtons, this is equivalent to 1 centimeter. So how many centimeters? 5 centimeters. So 1, 2, 3, 4, 5. So this 5 centimeters represents the length of the arrow represents our magnitude of a vector. And this head represents our direction. So our force vector now can be represented by this arrow of a vector. So how about parallelogram method? In parallelogram method, for parallel vectors, parallel can be added automatically. Example, if you have this, 5, the same. If you have F1 is equal to 5 Newton eastward, then added to another vector F2 plus 3 Newtons still eastward, going east. So this simply means that you are to add the 2 directly. So since they have the same direction, so 1, 2, 3. This is our F2, and this vector is our F1 for our example. So therefore, the F resultant is simply you add 5 and then 3 plus 3, simply 8 newtons. What is the direction? The same, eastward. So this is our answer for vector addition. That is if the two are parallel. How about antiparallel? So the antiparallel vectors are vectors in exactly opposite direction. What if our F2 is not eastward? How about F3? If F3 is 2 newtons westward. So therefore, if you're going to add vectors, F1 plus F2 plus F3, then what's your answer? So you have F1 simply 5 newtons, then plus 3 newtons. Since F3 is westward, then the opposite direction should be negative. So that's negative 2 newtons. So the result should be 6 newtons. Okay, what about vectors are non-parallel vectors? So non-parallel vectors can be added graphical method by, let's start with the parallelogram law. Again, remembering that the length of the arrow represents the magnitude of the vector. The direction of the arrow represents the direction of the vector. The magnitude and direction of the resultant vector can be found using an accurate scale drawing. So the parallel law states that if two vectors acting at a point are represented by the sides, so represented by the sides of a parallelogram drawn from that point, the resultant is represented by the diagonal which passes through that point of the parallelogram. Example, if you are given this vector A and you have a given vector B, then what's the resultant? So draw a parallelogram of this A from the head, drawn from the head of vector B, A. So this should be equal in length. So this is your A prime, the parallel of your vector A, and then B also drawn from the tip of A, following the same direction for B. So where the two intersect should be the head of your resultant vector. So drawn from their common tail to where the two parallelogram vectors intersect. So this now represents our resultant vector. Okay, another sample. You have your vector A, again the same in this direction. This is your vector A, and your vector B is in this direction. So what's the parallel? The parallel of A should be written from the, okay, this is B. This is your vector B, and the parallel of your A, how about this is your A, okay, from the tip of, so that's the parallel. This one is the parallel of A, and this is also the parallel of B. So where the two intersect should be the head of your resultant vector. So the resultant vector is this. From, this is your the tail of your vector, then to the head of your, where the two intersect should be the head of your resultant vector. This is your vector R, the red one. So what if there are two or three or more vectors being added? Example, if aside from A and B vectors, you have vector C in this direction. Vector C. So you're going to add, your resultant now is equal to A plus B plus C. So you're going to add first A and B, then the resultant R is not anymore the R total resultant, since you still have vector C. So this is labeled as R A B. So the resultant R should be the A plus B plus C. So what you're going to do, draw a parallelogram of this R, RAB, from the head of the vector C. Draw a parallel of RAB, and also draw a parallel of vector C. So the same manner, where the two intersect should be the head of your resultant vector R. So this now is your resultant vector AB plus C. This is now your R, or this R, and the A plus B plus C. But there is a simpler way. If it is two or more, three or more vectors, instead of a parallelogram law, you can use the Polygon method. The Polygon method, or known as a head-to-tail method. So it states that the tail of the second vector should be connected to the head of the first vector. Where's my first vector? And the tail of the third connected to the head of the second, and so on. So meaning the tail of the fourth connected to the head of the third. So in short, sumpay-sumpay lang. So but then the resultant vector should be drawn from the tail of the first to the head of the last vector. So let me give you a specific example. You have given A, vector A, meaning in general, it could be a displacement vector, force vector, acceleration vector, or whatever, as long as it is vector. So let's just represent that as vector A. So given 2 units, 20 degrees north of east. And then for vector B is equal to 3 units straight north. And vector C, you have a sample 4 units, 30 degrees south of west. Okay, so again, this represents general vector. But example, if the vector is displacement, you can write 2 centimeter or 2 meters, 20 degrees. So all the units become the unit of displacement. Now, if it is displacement, if it is a force vector, the units now become Newton because that's for force units. So let's now add these vectors using Polygon method. Okay, so you are going to use a scale. Example, for 1 unit, this is equal to 1 centimeters. So therefore, the 2 units are 1 centimeter. For 2 units, this is equivalent to 2 centimeters. And also follow the direction. So let's do the polygon method. Let's solve for R using A plus B plus C in this order. But addition of vector can be associative, commutative. So you can also have different arrangement. You can choose also to solve for find the resultant by adding first B plus C plus A. So regardless of arrangement. Okay, let's go to our polygon method using the head to tail, finding the resultant vector A plus B plus C. So in here, as you can see, you have from initial position, that's our initial position, and following the direction 20, and then we have in here 20 degrees north of east. So this is our north and this is east. So meaning from east covering 20 degrees. So this is now the direction of our vector A. So from here, follow the direction. What is the magnitude, the length? Only 2 units. In here, we have 2 units. So from here, 1, 2. So the magnitude is 2 units going 20 degrees north of east. And then from the head of the first vector, let's connect the tail of the second vector. So sumpay. So this now the starting point of our vector B. Our vector B is going straight north. So straight north. So how many units? That's the magnitude. So 3 units. So 1, 2, 3 going north. So this represents our vector B. Then the head of B would be our tail, the starting point or the tail of our third vector, the vector C. So from here, following this direction, 30 degrees south of west. So what's the magnitude? 4 centimeters. So from the tail of the first, where's our first vector? Vector A. So this is now the tail of the resultant vector going to the head of the last vector. So our last vector is vector C. So let's connect from the tail going to the head of the last vector. So this is now our resultant vector R. Okay, so what's the direction now of our resultant vector? So if this is direction is east, west, north, and south, then our resultant vector has this angle theta. So R therefore is equal to, depending on how many centimeters, and using your protractor, measure how many degrees and also supply the blank in here, how many centimeters. This represents the corresponding units. How many units? That's the magnitude. This is the magnitude of our resultant. And the angle theta. And then what is the direction now? theta, basing the theta, it is the theta degrees going north from west. So therefore, north of west, because this is direction going north. So this is now our direction for the resultant vector. By the way, there's a difference between north of west and northwest. Your bases should be from north to west, but north of west should be from west going north. So that's makes the two different, the northwest and north of west. So if it is of, meaning this should be the base, and if it is direct northwest sample, so the north should be the basis. Okay, but if north of west, west should be the basis. So what if the order is b plus c plus a? Would this resultant vector give the same r in here? You can try for yourself. So this r in here should be the same. The resultant should be equal to our resultant here, because regardless of arrangement, the resultant should be the same. So you can practice